Alright, welcome everybody. So today I'm going to talk to you about bonding in solids, and we're going to discuss the four types of solids and the bonding that's within them. We're also going to do some IB specific stuff with allotropes for carbon. So bonding in solids, the first type of solid is ionic solids, and we've talked about these, especially with lattice energy. Ionic solids, they have these positive and negative ions. Those positive and negative ions are paired together in an empirical formula. The idea is that the charges will balance each other. Now these ionic forces, they're really, really strong. So when you have an ionic solid, you're going to have high melting points. They're going to be stuck together in such a way that they will not conduct electricity when they're a solid. They're going to be extremely hard, and they're also going to be brittle. And this brittleness comes from the alignment of the ionic charges. And so when you hit a ionic solid, then when you hit an ionic solid, what you see is that the ions misalign. And when the ions misalign, they'll sort of break apart. And I'll show you this with a model in class so you can see what I'm talking about. Also notice with ionic solids, they'll conduct electricity when you dissolve them or when you melt them. And the reason why they'll do this, why they'll conduct electricity when they're either dissolved in water or they are molten, is because now these ions that were locked up in this lattice are now mobile and they're free to move around. The other type of solid is a metallic solid, and we'll talk a lot about metallic bonding, especially with the element tungsten. But, metallic solids, they are held together by these powerful forces, these metallic forces. But the electrons are free to move around, they're mobile. And what you've learned before about these metallic solids is that they have these delocalized electrons. But you didn't really learn about something called valence bond theory with the electrons in a metal, and that has to do with the idea that these orbitals form something in the metals, form something called a molecular orbital. And a molecular orbital, all of these orbitals will come together in what's known as a band. And the band of orbitals that forms will allow the electrons to move throughout that band and allow the metal to conduct electricity. Now we'll do a section on metallic bonding in the next video, but here I'm just introducing it. Okay. We also have molecular solids and covalent solids. Now the similarities between these two solids is that they both contain covalent bonds. So when I have a molecular solid, I have a substance that has a covalent bond. They have a covalent bond. But the properties of the solid are really defined by the intermolecular forces. That's what's important here. The intermolecular forces, that's what's holding the molecules together. So the molecules have these strong covalent bonds, but between the molecules they're held together by these weaker forces. And we discussed the weak forces in the previous video, and we did a lot of practice in class. But the idea is that these intermolecular forces, they determine things like the melting points, the conductivity. Because there's no electrons that are free to move around, and because there's no ions, these substances will not conduct electricity. There are a few exceptions to the molecular solids conducting, something like an acid in water, and that's only because an acid can break up into ions when it dissolves in water. But if we had something like hydrogen chloride gas, there's no free ions or no free electrons to conduct electricity. Now another type of solid that has covalent bonding in it is called a network covalent solid. And in these network solids, all of the atoms are bonded together throughout the entire substance. So there's no separate particles present. All of the atoms are bound together. And this creates this macromolecule in which you have some really unique properties to only things that are covalent networks. Here are two common covalent network solids that you should know and know a lot about. One of them is diamond on the left here. And diamond on the left, we can see that all of the carbons, if I highlight them pink here, all of the carbons are bound together in this tetrahedron. This makes diamond extremely hard. So it's a really hard substance, and it also has a very high melting point. Now, since there's no delocalized electrons or ions in in diamond, there will be no conductivity in diamond. most network solids, they conform to diamond's sort of hardness and high melting point. But we look on the right here, and this is another network solid, another allotrope of carbon, which is graphite. And when we look at graphite, what we see is that now there are these sheets of carbon atoms, and they're arranged in this benzene ring here, with the 6-membered ring. But the thing about this, about graphite that makes it different from diamond, is the fact that these sheets have delocalized electrons between the sheets. And so the electrons between the sheets here, which I'll highlight, actually let me use a different color, these electrons here that I'm highlighting, they're mobile. And so graphite can actually conduct electricity. And that's something that's unique to graphite compared to diamond. Now, with graphite, those mobile electrons also allow graphite to be used as a lubricant because of those mobile electrons. And so people will use graphite as a lubricant. Okay, this is showing you the metallic bonding with the delocalized electrons, and I'm going to again hold off on this until I do metallic bonding. Here are the types of solids, and what I like about this chart is that it really gets right down to what you need to know. It tells you the type of solid on the left, then it tells you what they're made up of, it tells you what forces are holding the different atoms or molecules together, it tells you the properties that result from that, and then it gives you examples of each. They don't expect you to really memorize covalent network solids, at least not in AP. In IB, they want you to know diamond, they want you to know graphite, but they don't really expect you to know that in AP. But in AP, they'll have a substance that's covalent, and it'll have a very high melting point. And they expect you to relate that to the fact that it is a network covalent and that it is all covalently bonded atoms together. So the last thing that I want to do with you is, for this video, is specifically related to IB. And so we talked about graphite and its properties, and two of the properties that they expect you to know for graphite is the idea that, one, it conducts electricity. It's used as a lubricant in industrial processes because of those mobile electrons, and both of these result in the fact that you have these mobile electrons in these pi bonds. They also expect you to know that with graphite, that there's this sp2 hybridization and this trigonal planar geometry. Now, two new ones that you might not have heard about that are specific for IB, and you can find this on page 119 of your textbook, are graphene and a Buckminster Floor, a C60. So with graphene, this is actually a really interesting molecule. So it's actually just, it's actually the first crystal that is two-dimensional. And that means that it's just a flat sheet. And actually, if you think about graphene in the terms of graphite, graphene is just one layer of graphite. And so it will have some of the properties of graphite, like, for example, it will conduct electricity, and it can be used as a lubricant. And so that's kind of cool, but something that's really interesting about graphene is the fact that it is about 300 times more conductive than copper. And so people are looking into, like, what can I use graphene for? And so some of the ideas are things like, LCD displays, things like computer displays, because of the conductivity. People are looking into it for, aerospace uses, and that's because it is much lighter than conventional metals, and yet it conducts electricity and has really one of these incredible strengths to it based on this type of bonding. The other molecule that they bring up in the text for IB and that they ask about on the exam is a Buckminster Floor. And this actually is a fullerene that has a soccer ball shape to it. And what I find most interesting about Buckminster Florenes is the fact that they're used for drug delivery. So what I mean by that is, let's say that you want to target a cancer cell in somebody that's suffering from cancer, and you don't want all those side effects. If you can encapsulate the drug within the Buckminster fluorine, then it can be delivered to the cancer site specifically and fight the cancer. Buckminster fluorines, they have this, I believe they have the same type of 6-membered rings that you see in graphite, so I think they are also sp2. And the difference with a Buckminster fluorine is that they do not conduct, so they're non-conductors. They're also non-polar. So if you want to dissolve Buckminster fluorines in something, you have to dissolve it in a non-polar solvent. And then we have diamond. And diamond we really spoke about a lot, but diamond's one of the hardest substances that we know. It's a non-conductor. And it has that sp3 and tetrahedral geometry. So those are the allotropes for carbon that they expect you to know. You can read more about this on page 119. So that's what I'm going to talk about for today. These are the types of solids. Hope you liked the video. Tomorrow in class we'll have some practice, more intermolecular forces, more stuff with solids. Thanks so much for watching.